Good afternoon, folks. Today we're going to be talking about how to do sort of like a quick estimate of the heat transfer coefficient for the jacketed reactor. Like, what is the UA value uh, based on perhaps on the volume of the reactor? And as I'm showing here, the heat transfer coefficient, which is namely the global heat transfer coefficient, U, in the unit that I prefer, which is going to be watt meter square Kelvin, and the transfer area will be meter square. So when you multiply both, then you get that famous UA that you can use it for uh, when you are writing, for example, differential equation for heat extraction, or you are adding heat or extracting heat from the reactor, etc., etc. So that factor will come out time to time. Here I'm showing you typically a laboratory scale of a reactor with jacket. Okay, so it's kind of nice. I used to work in a pharmaceutical, so I'm very familiar with both cases. This type of vessel, which are mostly in the pharmaceutical area, are mostly glass-lined reactor, just because we work with very highly corrosive material, and that's one. And the second big issue on this is that you want to avoid contamination of your product as well. So that's why you have pretty much kind of a glass-lined type of reactors. We'll go for the second slide here. So more of those equipment that you see in the laboratory, in where you can see clearly the jacket and the reactor itself. This need this needs the flange and the clamp for the top part. This one is like a whole unit, integrated unit with the jacket and the reactor. And these one are more like, I would say, more like into a pilot scale, but they have a computer, and they're kind of nice because they go into what I would call kind of a calorimeter type of analysis. You can definitely analyze pretty good uh, when you have exothermic type of reactions, and they are very good for doing kind of a I would say HAZOP analysis. What if situation, like what if I don't have enough cooling and there's a secondary reaction here that will kick a very high exothermic reaction. So things like that can be analyzed with this. Based on that concept, I used to work in my lab with equipment like this one. This is what we call the RC1. This is a pilot scale type unit. Uh, but before getting here, it's good to have a very good idea of what your reaction will be doing, right? Whether they have kind of an exotherm, or whether they will kick a kind of an exotherm type of reaction that you're not aware of, which is the problem when you are not aware. Because when you know that there's going to be a huge amount of heat produced, then you are prepared with the proper jacket sizing and everything, just to uh, reduce the temperature, just in case. But you need to know first. And so this come from the fact of an equipment like this one. This is what is called the RC1. The RC1 is from Midler, Toledo, I believe, and that was a long time ago, many years ago. I used to have this kind of equipment just to be sure that I fully understand the chemistry of some of the reaction, how much heat that can generate, and have a good idea of what uh, UA type of parameter I need to remove the heat that this type of reaction might produce. Like, for example, during an addition of reactant to something that is already here, that will generate some heat, and you have to remove that heat. So you want to be sure that you have the proper UA factor at your plant facility, because this is sort of like a scale down of what you are doing at the production level. Okay, and this is kind of a computerized, which is great. More into it. like for example, you can have uh, uh, vessels that have a split jacket, what I call split jacket, one jacket at the cylindrical portion and and a secondary jacket at the dish part, or you can have a full jacket like showing here in this reactor. This is more in line to what I used to do. This is a glass liner reactor. Our reactor were blue. They either come white or blue. Our were blue, uh, and so and the reason there's a reason behind why they're blue, because our product at the end, right at the end when we crystallize the product, is white. So if you see blue in your product, you know that your glass is broken, something bad is really happening. But if it happened to be white, it's harder to detect. So that comes along those lines. So anyway, here's a tank entry. There's a guy here checking the baffle, and so there's a huge protocol when there's a man inside one of these vessels. I mean, the protocol is kicked in, and there's several people involved to get this done, properly with a lot of safety to ensure that any of these this agitator will never turn on while there's a guy inside the vessel. So again, that's what we call it. It's called tag out, lockout type. So you kind of close the switch for this guy. You put a lock on it, and this guy might have even the key for that lock. So nobody can use any lock. Any key to open them up. The magnetic switch where the starter for this agitator is located. Okay, that's another story. I just talking a little bit about safety. And sometimes you have to get into this vessel to ensure that the glass lining is correct. Sometimes you do that with high voltage discharge just to ensure that there's no tearing within the glass line vessel, things of that nature. So that used to be done during shutdown. We run through the whole year, and there was a few weeks here and there that you have the opportunity to, do a good check on the vessel integrity. So here we are. We need to calculate the area of the vessel, the area for heat transfer. And most of these vessels have a very typical design. It's a cylindrical portion as shown here with a diameter D and a length L. But there's this portion here at the end, which is called a torus spherical dish. You can read more about it on this web page. But the idea is this, that the total volume that this vessel will do, which include the dish and the cylindrical portion, will be basically this equation as shown here. This part here is sort of like a rule of thumb for the torus spherical dish. It's a little bit more complicated than that, but it seems like it works pretty good. Pretty good. It gives you a good, and you will see in a second how good it is. And the cylindrical portion, the area times L. Now, the L over D is a ratio, and again, it just happened that where I used to work, that LD was mostly about 1.1. That was very typical. If I said it's 1.5, I can then take this L here and use this formula here and have everything in terms of D. So I can have the volume of the vessel all based on the diameter of the vessel. In a more general sense, if I don't know the LD, I can, if I know the value, the LD, I have this general expression, because if I happen to know the volume that I want, let's say that I want 100 gallon, 2,000 gallon, or whatever number, the number will come out here. Now remember, that number has to be either in cubic feet or cubic meter, so this to work out okay. Now, when you know the diameter of the vessel, then the other part is easy. You know the diameter, you know the L value, then you know the area of the cylindrical portion, which is this part here. Now, you need to add the area of the spherical part here of the ditch, which is sort of like a little bit of increasing the diameter of the vessel. Yeah, the vessel comes with a diameter, you multiply by this factor, and that's how you get the area of the bottom. So at the end, the total area for heat transfer will be the sum of this area here and this area here, which is showing here. This is shown uh, in this formula here. All right, so that's how you would do. Talking about baffle, there's a lot of story about baffle. Baffles could be like this one shown here, which is have a spiral baffle jacket, which has these I would call fins kind of soldered to the vessel, to the internal part of the vessel. So when the flow inside the jacket, it has to go through this little clearance space, so that allow a good mixing, and there's not going to be any short circuit between when it get in and eventually when it come out. So it's good mixing that you have, and that improve a lot. Having this spiral improve a lot the heat transfer coefficient for the jacket side. All right. Again, that has to be, let me put it back here. Compare with this one that you don't see anything. Sometimes it's just empty. There's nothing there. All right. But this one is another type of jacket. We have full jacket, no spiral baffle, full jacket with spiral baffle like this one. Okay, that show this. Now, spiral baffle has other parameters like, for example, the baffle pitch, which is the distance of one section to another, and so forth. All right. In my case, particular case, we're going to be working with this vessel. This vessel, our vessel were bought basically from this company, the Dietrich. I think I might be wrong. I think it's a French company, the Dietrich. Long time I don't work on the pharmaceutical area anymore, but I think it's a French company. And it just happened that this blueprint here is for a 2,000 gallons jacketed glass liner reactor, which was one of the many that we use in our pharmaceutical plant. So it's kind of nice to see this again. The last time I saw one of these was in 2007 or so, a long time ago. Anyway, so here is a little bit more detail of it. You have, like, for example, the L value is about 84. You have the internal diameter, it's about 77 inches. You have the internal baffle, it shows this both here. It shows the size of the agitator, 33.5 inches. The 125 RPM, variable pitch, and so forth. You know, quite a lot of information. You can, I can extract all that information because sooner or later I will need that information to estimate either the area of the jacket and the overall heat transfer coefficient. Like, for example, the volume of the tank is 2,000 gallons. That's what I call nominal value. The diameter, internal diameter of the vessel is 77 inch. The length 84. That gives you a LD 1.1. The external diameter of the jacket is about 83, and the space about 3 inches. That's this space here, about 3 inches. The agitator diameter is 33.5 inches at 125 RPMs. The inner shell thickness, and that is this inner shell here. This is the part that I'm talking about. It's about 1 inch carbon steel, and it's kind of nice. They give you also the jacket heating area, the total, 192 square feet. Now, let's do a mathematical check just to ensure how well our formula will provide something that is on these blueprints, okay? Some of the data that is already here. So let's do that. I'm doing that right here. Now, as I said, the volume of the reactor is 2000. I need, since I'm using cubic meter, then I have to change the volume here, the 2000 into cubic meter, which is what I did here. 7.57, the 1.1, that comes from the LD, and that will provide me the diameter of the vessel, which happened to be 1.97 in meter, but in inches, about 77 inches, which is basically the inner diameter, is right there. How about the length? 85. I got here 84. That's perfect. How about the area of the cylindrical section? Give me a number. How about the total spherical part? Another number. If I add up these two areas, it gives me 17.37 meters square. If I convert that number to square feet, 186, 192 as per the blueprint. Oh, not bad at all. I mean, I'm very, very, very close using just this a little bit of math as shown here. So I can, if I don't happen to have the blueprints, I can still approximate the values of a vessel as long as the vessel follows some conventional design, which is basically the total spherical dish at the bottom and a cylindrical part at the after the total spherical part. All right, that will do. Let's see what else. How about to calculate now the overall heat transfer coefficient? Well, you have to know a little bit of heat transfer, and definitely this is not a full course on heat transfer. This is more like a very, very 100,000 feet level looking down. So, and what I'm saying, let's say that I'm going to cool my reactor. This side is this temperature here is at the inside the reactor, and this temperature is at the jacket side. All right. So basically, you have convective heat or heat transfer coefficient that drop the temperature to the temperature at the wall. Then there's conductivity at the wall. Let's say that this is the glass line, and that this one is between the glass and the metal, and the last one is the metal. So this is glass line, and there's a resistance between the glass and the metal, which happen to be 0, because when they do this lining, they do such a, I mean, it's a marvelous, totally very interesting how they do lining, glass lining on this type of reactors, you know. So this resistance has to be 0. Now you have now the metal, which is about an inch, and eventually from there, then you have another heat transfer coefficient that has to do with the jacket side. So as I said, value, resistance value, that eventually, if you know each of them, you will come out with the global value, which is what we need. What is the global value? The U. Okay. Now, to do that, I like this web page. This web page is a chemical engineering calculation for how to get that U value, and it's kind of straightforward. It's divided in 3 sections. One of the sections is, let's see if I can pop this a little bit higher. One of the section is just data for the vessel, like the diameter of the vessel, what material you're using. The bad part here is that they don't use glass. I mean, but you will see in a second that there's a way to work that out. And the other part is, how about the jacket side? Here in the jacket is annular, no baffles, no spiral of anything, simple. The diameter of the jacket, this is the outside diameter. The flow rate, I'm using meter. The flow rate, I keep it as a gallon per minute because it's easier for me. The fouling factor, jacket is important. The density, about 1,000. Viscosity, about 0.01 centipoise. a little bit higher. These are default values. Some of these come directly from the web page. You can change it as if you know precisely the temperature are you going to be working on. Specific heat 4.18. Conductivity of that solution. Uh, I mean, again, this is I believe this is close for water. The viscosity 0.01 centipoise, and that will give you the heat transfer coefficient for the jacket side. Now for the tank or inside the vessel, that's highly dependent on the RPMs. So and the size of the agitator and the type of agitator. So you can pick those. Now here you see a fouling factor very high, 0.0002. I will say that this value should be 0.0025, but I kind of screwed up something here that I was doing. Basically, this fouling factor, the one that I'm using here inside, is for the glass line, which is basically the thickness of the glass, which is about 0.002. You have to divide that by the conductivity of the glass, which is about point 0.8. That would be about 0.0025. So I missed the 5 here. That's all. It would change a little bit. This number definitely would change it a little bit. This one here, but that's what I got. I realized that later, but anyway, I missed a 5 here. How to handle this web page? Let me do that in a second. So here we are in this web page from the chemical engineering calculation, and basically this one is kind of neat because it's kind of summarize how you go to calculate the overall heat transfer coefficient as shown here. Basically, as I mentioned before, it determines the resistance value of the jacket part. You add the fouling factor, you add the conductivity resistance part, you add the fouling factor of the vessel, and you add the resistance part of the inside of the vessel. And when you add up all that together, it will come out with a value. I mean, I've just opened this web page, and I need to do what is being shown here are the default value for this web page. So the first thing I will do is just go to the units and start to set the unit as I would normally do. Like for example, I'm okay with pounds per cubic feet. However, I might change to kilograms per cubic meter. How about the specific heat? Can also change this one to metric unit. Thermal conductivity, let's change it to I'm okay with inch. I'm not using pipe. I'm going to be using a full jacket. How about flow rate? This one I really like it the way it is in gallons per minute because it gives me an idea about size. For example, if I hear a flow like about 2 gallons per minute, I know that's sort of like a flow for a home, for a house, about 2 gallons per minute. But if I hear something like 30, 40, 50, well, that's a kind of a plant size type of flow rate and so forth. How about this one? I can change it to, let's see, diameter, length. I'm not sure it was in, no, I want to change this to meter. That will do, diameter and length. How about velocity? Meter per second. Heat transfer coefficient. I'm okay the way it is, but I'm going to change this as well to a metric type of unit, and so the fouling factor also we'll change it to metric, and that will do. Only basically leave the flow rate. This is the one that I rather keep it in gallons per minute. That will do. So I guess now the default value will change to according to the unit that I set into my system. So I brought this sticky note here, so I have some numbers for the vessels that I was studying. The Dietrich 2,000 gallon vessel. And the internal diameter, which is this one, let's change it to 197. Uh, what else here? Stainless steel. Well, actually, this is carbon steel. The thickness of the metal is about 1 inch. This is still 1 inch, so let's right here 1 inch. And now let's see anything else here. The jacket side is a full jacket, no baffles. I mean, it's a big difference when you set this as spiral baffling or not. It really makes a difference. The one that we are talking about has no baffles, so no baffles. Now the jacket outside diameter is 2.12. 2.12. Now the pump, the flow rate through the jacket. I mean, I'm going back to my experience when I was in pharmaceutical plant, and typically it was about between 30 to 50. I will use the lowest, 30, and I will leave the fouling factor the way it is. I can increase it definitely, but that's okay for me for now. Let's see, properties. Let's say that I'm using kind of chill water at the jacket side. So I have here sort of like some numbers, one at 40 and one at 10 degrees. So density, I will keep it about 1,000 kilograms per cubic meter. You know, let's put 1,000 here. And how about the viscosity? Well, the viscosity, here's mu. I have two values, one at 40 and one at 10. As I said, let's say that I'm at 10, so that will be 1.3 centipoise. 1.3 centipoise. How about the specific heat? Well, this should be about 4.18 in this unit. How about the thermal conductivity? Thermal conductivity for water at 10 degrees will be 0.578 on this unit, watts meter Kelvin. So let's change this one to 0.578. And I'm saying basically that the jacket is about 10 degrees, and I'm cooling the reactor, basically. That's what I'm saying. The wall viscosity will stay at 1.3. I will not change this one. Will stay the same, 1.3. I guess that will get all the data that I need. Let me check one more number here. Jacket or coil length. In this case will be jacket length. 2.13. That will do. Oops, I thought that I changed this to 30. Now it is. Okay, so that's the flow rate, 30 gallons per minute. Fouling, I leave the default value. The density 1,000. Viscosity 1.3 at 10 degrees. Conductivity, thermal conductivity 578. 1.3 at the wall. I think that I got everything that I need. Again, checking annular, no baffles, good. The outside jacket diameter. Let's see if I got all here. Yeah, 2.12, and the length 2.13. That sounds super. Well, that will provide me the heat transfer coefficient for the that will be for the jacket part. 59.72 watt meter square Kelvin. Kind of low on the jacket side. Probably because there's no baffles within that section. How about here? Carbon steel, 1 inch. Yep, that sounds super. Let's take a look now at the agitator side. Let's change this glass steel. How about the diameter of the agitator? It's here. No, it's not. It's not on my sticky note. So, but I remember, I think it was 33.5 inches. Actually, I can double check on my here. Let's see, 33.5. Yep, I can stay. Let's move the sticky note to the one side. Yeah, it's a glass lock span editator with two separable variable pitch plate, 125, 33 and a half span. Well, that will do, 33 and a half. So let's go back to here, and I got that 33.5 inch, RPM 125. Fouling, I will leave it the way it is, although I will do a minor change. How about the density? Well, let's use water. The viscosity, water at 40 degrees is about 0.65 centipoise. The specific heat, that's about 4.18. Thermal conductivity is about 0.628. Oops, 2 point here. There we go. The wall viscosity, I will leave it the way it is, about 0.65. And I guess I got pretty much that I need. Reynolds, Prandtl, and that will provide heat transfer of about 3,000. I mean, it's highly dependent of the RPM. If I drop the RPM, let's say to 50, that number will change. See, almost half of it. Let's go back to the maximum. That would be 125. All right, that will do. So I got pretty much everything. I got the vessel heat transfer coefficient, the jacket heat transfer coefficient, and I just need to add them up with the different resistance value. Like for example, this one here will be the resistance value for the jacket side. That will be 1/59.7, and so the fouling factor. And so the X over K, thermal conductivity for carbon steel, and the X is 1 inch here. Now, here's the story. This website doesn't have for glass lined reactor, but that would be easy. It's like adding another resistance value. But there's no way here that I can add it. But you have the fouling. Let's say that the actual fouling, this is a glass lined reactor. Let's talk a little bit about this. Fouling in a glass lined reactor will be 0. I mean, you clean the vessel and you go back to the original basis. So shouldn't be a problem. Now, at the jacket side, the jacket will be another story here. As the jacket is being used, more accumulation start to get there, and that would be a problem in the long run. So you need some time to do a shutdown and clean those jackets properly. Now, going back to the fouling factor of the reactor, I would say this is 0, except the lining of that glass is about, the thickness of that lining is about 2 millimeters. So to make the story, oops, I think that I erased what I'm not supposed to. I think that was 2.12, I believe. Yeah. If I do the calculation here, that's what I mean, was to do, like, for example, it's like taking, not that it's gonna be done here, but just for illustration, would be like taking the thickness of the glass, which is 0.002, and divide that by the thermal conductivity of glass, which is 0.8, and that will give you, it's not that, actually that's not a fouling factor, but it will be like the correction that you need for the conductivity of the glass, or the heat conduction. So in that case, just put the right number here. I think that I have it here, X over K for glass, that would be 0.0025, and that's the conductivity, the correction factor for the glass that I have, the lining that I have. So it's like adding another of these the way it is. So I pretty much got everything here, and that will eventually add up to a final value of about 49 watt meter square Kelvin, which is kind of, I would say, kind of low. It's not bad. It's not bad, but it's low. It's just because I don't have baffles. If I change this number, I mean, if I change that instead of having this, I have spiral baffle, that the number will definitely will get better. But at the since I'm entertaining the concept of using this type of vessel with no spiral baffles, that means that is the way it is. With that said, let's see how this end up. Like for example, going back here, I'm gonna use the 49, which is the calculation. I'm doing a quick check just to be sure that I have everything. 197, carbon steel, 1 inch thick the wall, annular, no baffles, jacket outside diameter 2.12. The length of the jacket is 2.13. Actually, I got, well, yeah, 2.13. This one here is, I think that I screwed up. That one is 2.13. That's correct. The flow rate 30. The maximum will be 50, typical, but that I will not. I mean, let's see. Let's put the 50. Let's see how, if it get a little bit better. Well, actually, it does, but by very little. It increases to about 60. Let's go back again and put 30. Let's see, 30, 49 versus 50, 60. Very little. All right, so let's go. Let's see the one that I'm only about 10 more watt meter square per Kelvin. But this is the typical flow for our jackets when I used to work at the pharmaceutical plant. Now, I think that I got pretty much everything that I need here. I think the numbers are correct. I mean, at that flow rate, it's going to be a laminar flow, very little mixing, very far away from being a turbulent flow. The heat transfer is very low, 59.72, very, very low on the jacket side. But that's what we got. So that's going to be 49. This is the number that I finally got, 49.21. And let's write that number here, my sticky notes. So finally, the overall heat transfer coefficient that I got is 49.21 watts meter square Kelvin. And that's it. So with that number, I can go now with that number and go to Excel for 1 second here and finish some of the calculations. So I got this number here. Oops. That number is about 49.21. Let's fix this so it looks better. There we go. Center, that will do. And let's increase the size to about 14. That will do. So that's basically the heat transfer coefficient calculation. And now the U times A, that will be obviously this number multiplied by this number. And so let's do again a little bit of fixing so that looks better. And let's get this right. Center, that will do. So that's basically, I would say that UA is on the low side. But I mean, that's the way it is. So end up being about 854 watts Kelvin. that's about point 8, point 9 kilowatt Kelvin. I really like to see that number higher than 1, but that's okay. I mean, that's what we got. That was the idea. If we have a vessel, like, we want to have a calculation about how to get UA, this is a very simple way to do it. You just basically, the volume of the vessel, you run, for example, this vessel was about 2,000 gallon, so I convert that to meter, to cubic meter. I know the LD ratio for this vessel, for this tank, because I have the blueprint. If you don't, then you pick one of the proper LD ratio. I will tell you that 1.1 was pretty much all our reactors, which we have many of those. We have, I would say, like about, I don't know, about more than 30, about 30 tanks. And I would say that that was a typical ratio, about 1.1 LD ratio. They are glass lined, again, glass lined. So now with that and the volume, you get all this number. Like, for example, the diameter of the reactor, you can get this formula here. You get the length of the reactor, the area of the cylindrical area, the area of the total spherical dish here, and you add these two areas, you get the total area, the total heat transfer area. And this value, the global heat transfer coefficient, was from the web page. And again, here's the web page. I can, let's see if I can reduce it a little. One thing that I can certainly do is entertain what will happen if, instead of, I have everything the same the way it is, but instead of having, like, for example, no baffles, I add baffles like this, spiral baffling. Now, they pop more stuff that I need to take care of, like, for example, the width of the annular space, about, I would say that's about 3 inches. If I change that. Now, how about the baffle pitch? Well, I'm designing. I can pretty much use some numbers here. Let's see. The length is about, in inches, is about 84 inches. I will say a good separation would be about 12 inches, perhaps. Let's entertain 12 inch here. And I think that would do. Anything else that I need to change here? Everything else stay the same, the way it is. And let's see. You see how it increased it? Increased it a little bit, got better. Now in the turbulent region, that's good. And the value is higher. Now let's see whether it has a good impact on the overall heat transfer coefficient. Yes, it did. 141, a lot better. And that's changing. Obviously, it's a big change. Adding spiral baffling is at the design time when you are building the vessel. Either you have it with this type of baffle or you don't. The one that I was entertaining before didn't have the baffle, so the calculation was the way it was. But if I add baffles, then the number really changed. 141. I can put that on the sticky note here just to end this. But this value will be 141. Basically, I would say 142 for the sake of the argument. And that would be watt meter square Kelvin. So it definitely improved the overall performance of the jacket when it has baffle. Basically, I think that I cover everything that it has to be discussed with this web page. And the only thing, remember where this number come from. I kind of tweak the web page just so that I can incorporate the glass lining issue that it has to be incorporated. And the glass lining, basically, in pretty much all vessels that I have studied before, they're about 2 millimeters. Could be a little bit less, but basically they kind of everything would be around 2 millimeters, the thickness of the glass that they use. So that divided by the thermal conductivity of the glass, that will give you roughly this kind of fouling factor, which I'm just using because this web page doesn't have a way to add the x over k for the glass. It has the x over k for the thickness of the wall of the inner shell of the reactor, but not for the glass. So that's the way I just did it to fix that up. The other part is the way I entertain the fact that you could have a vessel with a jacket without baffle and with baffle. It makes a big difference. It makes a big difference, as you can see here on the U value. Well, that's it, folks. Thank you for your attention. Have a great day. Bye.